Welcome back to the Solving Problems in Jelly video series. So the problem we'll be looking at today is called Compute the Fibonacci Product, and it's posted by code golf user Jonah. So let's go over the background of this problem first. Basically, it comes from the Zeckendorf representation, which is based on representing each number as a sum of Fibonacci numbers. And in fact, we can show that every positive integer can be represented uniquely as the sum of one or more distinct non-consecutive Fibonacci numbers. I won't be going over the proof today. So given this representation, what does Fibonacci multiplication mean? Essentially, given two numbers a and b, we will convert them into their Fibonacci representations this way, such that a will be the sum of C1, C2, etc. for however many numbers are in its representation, and we do the same with b. And then we take the Cartesian product of the indices of these Fibonacci numbers and add them together. So let's do an example. For example, 2 is just the third Fibonacci number, and 4 can be represented as 1 plus 3, which is the fourth plus the second Fibonacci number. Notice that when we have 1 in our representation, we are using the second Fibonacci number and not the first. So then, to compute the Fibonacci product of them, we take the representations and take the Cartesian product. So for each element in the representation of 2, which is just 3, we add each number in the representation of 4, which is 4 and 2. So 3 plus 4 is 7, and 3 plus 2 is 5. So we take the 7th and the 5th Fibonacci number, which are 13 and 5, and we add them together to get 18. As a slightly less simple example, let's look at 4 and 9, for example. So 4 can be represented as 3 plus 1, which is the fourth Fibonacci number plus the second Fibonacci number. 9 can be represented by 8 plus 1, which is the sixth Fibonacci number plus the second Fibonacci number. So now to take the Fibonacci product, for each element in the representation of 4, we will add each number in the representation of 9. So we have the 4 plus 6th Fibonacci number. Because of that, we have 4 plus 2. And then we have 2 plus 6. And then we have 2 plus 2. So this gives us the 10th Fibonacci number, which is 55, plus the 6th Fibonacci number, plus the 8th Fibonacci number, plus the 4th Fibonacci number. And so if we add those all together, we get 87. And that's the correct answer in this problem. So with this defined, let's move on to solving this in Jelly. So we'll want to take the two arguments as a list rather than as two arguments. Now with a and b, you might imagine that we'll want to take it as the first and second arguments and run a dyadic link. However, we first need to convert each number into its Fibonacci encoding, and it's much easier to do that by just running a large each chain over the entire input. So let's take 7 and 9 as our inputs, just for the sake of having a more interesting example. So here we'll be using the shortcut syntax close round bracket. As a reminder of what this does, it's equivalent to creating a new monadic chain and then immediately applying each to the previous chain. So as long as we don't use any chain separators before this, it essentially maps the entire chain before it, whatever is here before it, monadically over the entire input. So for each number, we're going to need to convert it into its Fibonacci encoding, and we want the indices of the Fibonacci numbers themselves, not the Fibonacci numbers, because we'll need to add the indexes together later. So in order to avoid the issue of having 1 and 2 be the same Fibonacci number, we will just drop the 1 entirely. Because again, since the representation is unique and doesn't have any adjacent numbers, we can't have 1 and 2 together anyway, and we always use 2 based on the way the Fibonacci coding works. So we're essentially just going to brute force this. We're just going to take every single set of Fibonacci numbers up to the nth number. And here's the thing though. The fifth Fibonacci number is, the second Fibonacci number is actually smaller than 2. So in order to find a set of Fibonacci numbers that sums to n, we'll actually need to look up to the n+1th Fibonacci number. However, that's pretty easy to do because we want to exclude the 1 anyway. So we can just take all the numbers from 1 to n, find the power set, which is the set of all subsets, and then just increase all of those by 1. And that simultaneously includes n+1 and drops 1 itself. So we're going to call the power set, and this is a very large output, but we can just see that basically the first sublist, and somewhere in the middle here, just gives us every set of numbers from 1 to 7. And then we will just increment the entire thing, and now we get numbers from 2 to 8, which will allow us to cover the edge case of the nth Fibonacci number being greater than n, or sorry, being smaller than n, and allows us to exclude the issue with duplicating 1. So now we want to filter these out to find every single one that is a valid representation. So the way we'll do that is we'll run a filter, and for each element in the power set, we'll convert all of the indexes to the Fibonacci number at that index, and then we'll sum them together. So we're going to use the filter quick, filter by condition. And what we'll have on the left, let's call it last dyad for now, and we will try to inline this later on. So what do we want here? Well, on the left side, we'll have the set of indexes, for example, 3, 5, 8. And on the right side, since we haven't specified anything, implicitly we'll get the argument to the chain itself, which will be whichever number we're currently working with. So we want to get the zth item based on each one. And so, just as an example, let's say we have a sequence 3, 5, 8. We'll convert it into the Fibonacci numbers, and then we'll sum them together. And then we'll check if it's equal to whatever is on the right. So for example, for 27, that would be false. For 28, that would be true. So we'll take this link, and we'll place it here. And this will filter the indexes to only keep ones that are valid encodings. So since this is just 3 atoms put together into a dyadic link, we can just use the last 3 links as a dyad quick and inline the entire thing into our filter. Now the other thing we need to do is remember how we need to exclude adjacent numbers. For example, we see here that 2, 4, 5 has adjacent terms here. So to filter those out, we'll use the increments atom, which will get the differences of consecutive elements. So we'll need to filter again. And this time our filter will be just a monad. So now, before we actually put our filter here, consider the way chaining rules work. We have a monad followed by a monad, and this entire link here is a dyad. So if we place another monad immediately after it, then it will form a 2-1 chain, which will apply the monad to the argument on the right side, which is not what we want. So in order to avoid this, we can use the identity on the right side. And so this becomes a 2-1 chain, such that on the left side we have each index set that we're filtering, and on the right side we have the input itself. And so now we can filter. And this time our filter will be a monad. So let's use the call as monad quick. And we'll want to take the increments and then check to make sure none of them are 1. Because power set isn't going to return a set with equivalent elements, we won't get zeros. So we just need to make sure there are no 1s. So there are a couple ways to do this. We could have used a filter out and then just check if any of them are insignificant, meaning any of them are 1 or less. We could also check if 1 is in the set, etc. However, filtering out takes 2 bytes because the inverted filter quick doesn't have a 1 byte shortcut. And so ideally we want to be able to filter in and have some condition that takes up 3 bytes that validates that there are no adjacent elements. And so the way we can do this is by decrementing. If we decrement all of our numbers, since they're all 1 or greater, then the 1s become 0, and everything else that's positive stays positive. So if we decrement, then we want to remove any sets that include a 0. And so we can just check if all of them are truthy. And if not all of them are truthy, then it means that we found a 0, which means that the original sequence had a 1 in its first differences. In other words, it has adjacent elements. And so we see that that removed the 2, 4, 5 now. This is just a chain of 3 monads being called as a monad. So we can use the last 3 as monad quick to group them together and inline this link as well. And so we could potentially be getting multiple elements on our list because we've basically taken the power set, filtered ones that have the valid sum, and filtered ones that don't have adjacent elements. So we could potentially have multiple possibilities. However, first of all, notice that the problem does say that they're unique, so we can just assume that we'll have a unique representation. And second of all, later on I'll get into why this part is actually unnecessary. But for now, let's just use the head atom to pop off the first item for each. So now we have a list of the 2 Fibonacci encodings based on the indexes for each number. And so to take the product, we will need to take the Cartesian product of the 2 and then sum each of them together. Or we can just use the vectorize at depth 1 sum. And this will sum every single pair of the indices from the first set and the second set together. You could also use addition with the outer product quick, but that produces a matrix of values which we then have to flatten. And so it's shorter by 1 byte to do this. And thanks to caird for observing this trick in their answer here. I initially was using the product table and then flattening afterwards, so I was able to save a byte using this. And so now we just need to convert the indexes to Fibonacci numbers and sum them together. And we see that this gives us the correct answer. So this here is a valid submission. And in fact, it's actually pretty much the same as caird's submission, except they did the filters in the opposite order. And instead of using identity to prevent the chaining, they just put the pop head off each outside of the loop chain itself. So now remember what I said earlier. This part here is actually completely unnecessary. And the reason is because popping off the head will get us the shortest valid power set, because power set comes in order of length. And we can prove that the shortest sequence of Fibonacci numbers that sums to n will not have any adjacent values. Now, why is this? Let's say we have a number, 9 for example, that has a representation consisting of adjacent Fibonacci numbers. So 9 is equal to 1 plus 3 plus 5. And 3 and 5 are adjacent. Well, since 3 and 5 are adjacent, and every Fibonacci number is the sum of the previous 2, then the sum of 2 adjacent Fibonacci numbers is just the next Fibonacci number. And so let's say we have a sequence of any number of Fibonacci numbers, like 1 plus 8 plus 13 plus 21. For any such sequence, we can take the largest 2 numbers that are adjacent. And since these are the largest 2, that means that the next Fibonacci number in the sequence cannot be in the sequence. And the reason for that is because otherwise these 2 would be the largest 2 adjacent ones. And so we take the largest 2 adjacent Fibonacci numbers and we just replace them with their sum. Now let's say we had 1 plus 13 plus 21 plus 55. These 2 are not adjacent. So we take the largest two adjacent numbers and just replace them with their sum. Now we might end up getting another pair of adjacent numbers as a result of that, so we just replace that with its sum as well. And so if we keep repeating this procedure indefinitely, each time we take the largest two consecutive Fibonacci numbers and replace them with their sum, then eventually we will arrive at a sequence that does not have any, and each time it gets shorter by one number. So this proves that any sequence of Fibonacci numbers where two are consecutive will not be the shortest or tied for the shortest of all sequences of Fibonacci numbers that add up to n. And so the shortest one, which will be the one returned first by power set because it comes in order of length, is necessarily the correct answer. And so we don't actually even need to filter by this condition of avoiding adjacency. And so we can just save those 5 bytes. And this is the exact submission that I submitted. And so I have an explanation in text under this answer if you are interested. And I also have an explanation of what I basically explained earlier with the procedure to shorten any sequence to prove that the shortest one does not have any adjacent values. So credit goes to code golf user Jonah for this very interesting problem, and credit goes to caird for helping me find a couple of tricks to save bytes from their answer here. So if you enjoyed watching this problem-solving video, please like the video and subscribe to see more content like this, and otherwise, thank you for watching.